This is the fourth video about the best methods for oxidizing secondary alcohols to ketones, where I'd like to present to you the Oppenauer oxidation. In Oppenauer oxidations, the oxidant is a ketone, which must usually be used in excess. Therefore, this oxidation is inherently less clean and more wasteful than the methods used in previous presentations. On the other hand, Oppenauer oxidations can be quite selective and a valuable alternative if the starting alcohol has a complex structure and is expensive. The Oppenauer oxidation is the reversal of the Meerwein-Ponndorf-Verley reduction and essentially an equilibration by hydride transfer between an alcohol and a ketone or aldehyde. Meerwein originally attempted to reduce aromatic aldehydes with ethanol and found that this could be cleanly accomplished with aluminum ethoxide. Alkali ethoxides could not be used because these were too basic and caused the products to undergo aldol condensation. Magnesium or calcium ethoxide were also much less effective reducing agents than aluminium ethoxide. Oppenauer initially used aluminium terzbutoxide as catalyst for the oxidation of alcohols with excess ketone, but later many other suitable catalysts were found. As hydride acceptors, a number of different ketones have been reported. Aldehydes are rarely used as oxidants because these condense too quickly with most ketones. The main advantages of the Oppenauer oxidation are its simplicity and the relatively mild reaction conditions. Because many other oxidations proceed under acidic reaction conditions, the Oppenauer oxidation may be the method of choice for certain acid-sensitive, base-resistant alcohols. Furthermore, the reaction is highly selective and almost only alcohols are oxidized. Even electron-rich functional groups, such as tertiary amines or alkoxyarenes, will usually remain unchanged. Unlike other oxidation methods, few volatile byproducts are formed during the Oppenauer oxidation, making it particularly well suited for the production of fragrances. One important disadvantage is the formation of stoichiometric amounts of an alcohol, which should be chosen so that its removal from the product is simple and effective. Sometimes large amounts of catalyst are required. This can be the case if an old batch of aluminium or potassium alkoxide is used, because dry alkoxides are quickly neutralized by carbon dioxide. If during an oxidation esters are formed, for instance by the Tichenko reaction, these may be saponified to carboxylic acids, which again may neutralize the catalyst. A further problem is the need of a large excess of organic hydride acceptor, which is inherent to this reaction because of its reversibility. This is an old organic synthesis example which shows that the aluminum alkoxide is a true catalyst. Less than one equivalent is enough to bring about a complete conversion of the starting material, cholesterol in this case. Although aluminum alkoxides are not strongly basic, the double bond migrated into conjugation with the carbonyl group, as often happens during the oxidation of homoallylic alcohols. In this example, geraniol was oxidized to citral, a common fragrance of many household products. As hydride acceptor, pivalaldehyde was used, which does not undergo Tichenko reactions. Only 2% of catalyst was required and the reaction was done without any additional solvent, what further improved the purity of the final product. As mentioned earlier, for the production of fragrances, it is important to keep the number of potential impurities as low as possible, because most of these will spoil the aroma of a fragrance. This here is a more recent example where trimethylaluminum was the catalyst and nitrobenzaldehyde the hydride acceptor. Interestingly, despite the excess of aldehyde and its high reactivity, no aldol condensation products were observed. These would probably be formed, however, if the reaction was conducted at a higher temperature or for too long. When preparing secondary alcohols from aldehydes and Grignard reagents, ketones are sometimes obtained as byproducts. These are formed by oxidation of the initially formed magnesium alcoholate by some hydride acceptor, such as the starting aldehyde or oxygen. In the example on this slide, a sterically demanding aldehyde devoid of alpha protons was added to a modified Grignard reaction, what caused the secondary alcoholate to undergo complete Oppenauer oxidation. This is an example of a ruthenium-catalyzed Oppenauer oxidation. Only a relatively small amount of catalyst was required and triethylamine could be used as base. The high temperature was required to achieve complete conversion in only 4 minutes, but batch processes can be run at much lower temperatures. This ruthenium-catalyzed Oppenauer oxidation seems to be mediated by a dihydride complex, which reduces the main oxidant and forms a ruthenium alkoxide. This complex can undergo ligand exchange with the alcohol to be oxidized to yield a new ruthenium alkoxide complex. The dihydride is regenerated by beta elimination of the target ketone. In view of the mild reaction conditions, this ruthenium-catalyzed Oppenauer oxidation could be particularly useful for sensitive, multifunctional alcohols. Besides the problems of removing excess oxidant and the alcohol byproducts from one's target compound, a number of side reactions can cause the formation of additional unwanted products. The most important side reaction is aldol addition and condensation of the produced ketone with itself or with the oxidant. This side reaction was the main reason why aluminum alkoxides were initially used as catalysts in the Meerwein-Ponndorf-Verley reduction instead of alkali alkoxides. The latter are too basic and promote aldol condensations too efficiently. Nevertheless, even with aluminum alkoxides, aldol chemistry can be a problem if the target ketone or the oxidant are too reactive. When preparing aldehydes by Oppenauer oxidation of primary alcohols, or when using enolizable aldehydes as hydride acceptors, a further side reaction is the Tischenko reaction. In the example on this slide, benzophenone was used to oxidize a primary alcohol to an aldehyde which underwent complete intramolecular aldol condensation with a ketone. A large number of different catalysts have been tested both for the Oppenauer oxidation and the Meerwein-Ponndorf-Verley reduction, as shown on this and on the next slide. Calcium and titanium alkoxides do not seem to work well, but for several other metals, including transition metals, successful examples have been reported. Here are some more examples of transition metal catalyzed Oppenauer oxidations, including noble metals. Although much less catalyst may be required, one shouldn't forget that ruthenium, for instance, is around 15,000 times more expensive than aluminum, and iridium is 90,000 times more expensive than aluminum. So, to compete with aluminum alkoxides, noble metal complexes would have to be effective at truly homeopathic concentrations.